We've covered series and parallel circuits, and now we're going to take a look at what we call series parallel. It's a combination of the two. I'm going to start with a source, and I'm going to put a series resistor in the line, and I'm going to put a parallel network. This is what we call a series parallel circuit, and they're very common. In fact, most of the circuits you work on more likely will be of this style. We have the current that's flowing through the parallel branch, and it's going to divide in between the two. And we have the combination of the two currents as they drive out here in the form of the total amount of current goes through the resistor, label this R1, and back into the power source. So the two different branch currents that are going through R2 and R3, they're going to be determined by the size of those resistors, and we call those current dividers. So as we're looking at this entire circuit, what we need to do, step number one, is convert this into a series equivalent circuit. Series equivalent circuit. I'm not going to go through how to calculate the total amount of resistance in series and parallel, but it's a combination of both of those with the idea that once this parallel connection, R2 parallel with R3, we're going to change that into a combination factor called R sub A. R sub A is the parallel combination of R2 and R3. When you're done calculating this part right here, it will then be added to R sub 1, and that will turn into the total amount of resistance for the circuit. And there's how the construct is for this particular equation. In a different form of this, let's take a look at a different form of this particular circuit. And we're going to keep our series resistor, but I'm going to come out here and put something at an angle, and another one at an angle. And it's kind of a half form of a delta resistive net. The way that we want to take a look at this is we still have current that's coming through this R sub 2 here, and we still have current that's going up through the R sub 3. It's important to keep in mind that although these are at angles, you can actually convert these back into the rectangular version. For example, if I disconnect R2 and R3 here, extend the line out, these connect onto the main branch line coming out, and it looks very similar to the previous circuit that we just studied. Same thing can occur here. I'm going to change this slightly. Same thing will occur right here where R2 is going to tie here, and R3 will tie here. We still have a parallel branch of R2 and R3. The solving of the total amount of resistance for the circuit so you can find the circuit current is the same process. It's just a way of revisualizing these two devices, and if we had a third one, we could actually put a third one in here. If I were to do this, let's take this and redraw it and see what this would be if I add an R sub 4 to this entire circuit. I'm going to take this series resistor, which is in series with R3, and convert that into a single network to make it easier to visualize. So we took the resistor that was lying down here in this part of the branch circuit, and we raised it up to take a look at it and see what it would look like to make this a little easier to conceptualize. And calculating the total amount of resistance for this whole circuit now, we're going to have R2, which is in parallel with the combination of R3 plus R4. So R3 and R4 is a series connected resistive circuit, but it is still in parallel with the other resistor, which is the R sub 2. So let's take a look at the expression. Remember that R2 is going to be in parallel with this particular network, and we still can refer to this as RA, or we can be specific as to what we have for different devices. Another thing that could be done is, after we take a look at the branch currents that are going through here, is that each one of these resistances is going to have its own voltage drop out across the entire network itself and out across each one of these. Because it still has current flowing through it, and also through R2, this branch current, when it's multiplied times the value of R3, gives you the voltage drop across it. The branch current multiplied times R sub 4 will give you the voltage that's out across R4, right here. This is a voltmeter. We went in to take a look at this. That's how we would take a look at the individual voltage drops. We would find out that if we added those two voltages, that we would actually come up with the voltage that's out across the entire network. And it goes back to our original premise that voltages across the parallel system is essentially the same for every one of the branches.